With the pleasure of having here Felix Willenborg from the University of Bremen. And we will talk about exact wave-optical imaging of black holes.
So I hope you can hear me very well. That's the case. Last talk of the day. Thank you for coming, and also thanks for inviting me to this workshop. I'm very grateful for that. So as already introduced, I'm Felix Willenborg from Bremen, and my research topic is like wave optical imaging, but in an exact an analytical way. And today I want to talk about some parts of my research where we take a look at wave optical image formation in black hole spacetimes. What was the motivation for this work? Our work group has some experience in the calculation of shadow boundary curves, and these are usually calculated by coming from a geodesic approach, and you are looking for boundary curves from an observer where these geodesics hit the photon region, and then you can make out the morphology of a shadow of the shadow of a black hole. So there are other approaches as well where you make lensing maps from exact spacetimes. So here you have a sphere where the observer is on the surface here, and on the other side is a white dot to indicate the antipodal position to that observer, and in the center we have a black hole, and then you get the right image. So from this you can see from which direction these light rays then come, and you can characterize the effect of the black hole so on the observer by this way. However, this is like a geodesical approach, so you won't get any kind of information of magnitude or something like that. So it is just telling you the direction in this case. I mean, the motivation is very clear here. We want to characterize measurements we already have made. And this picture you might not see the last time, so I just figured it out. It's nice to see it here. So how to calculate wave optical image formation in an exact analytical way. So the history of this topic is that we come from a scattering, and we want to have a point source which is being scattered by a hole. And usually what one does is like to introduce some approximations, for example, WKB high frequency approximations, or just brute forcing with numerical approximation and calculating it this way. And so the recent publications were focusing on the differential cross sections at an observer, or to calculate quasinormal modes. So, and I mean, we have one of the authors I cite here in the audience. So they calculated scattering in an analytical manner, but only in the presence of a cosmological constant. So much for the scattering. What about wave optical image formation in other contexts? So there are this geometrical approaches being used where an amplification factor, so to say, is being used where a phase is being transported along a geodesic, and then you take a look how the phase of this, how this phase by the underlying spacetime is being altered. So exact wave optical image formation. Exact wave optical image formation is missing or was missing, and these are results now where we try to calculate it this way. And how a wave optical image can look like, or a wave optical shadow of a black hole, I want to spoil at the beginning. So what you can see here, for example, is our point source is being scattered in such a way that you can see a wave optical image formation at an observer. So it is the absolute square of the Fourier transformation of the Green's function, so the Green's function describing the scattering of the point source. So, but how to get to this result? The table of contents I want to talk about in order to get there is we first try to use the Kerr-de Sitter spacetime, and we will use linear perturbations in the Newman-Penrose formalism. This means the Teukolsky equation will come into play. And the solution of such an equation is described by the differential equation, which is called Poincare equation. And then we describe the solution of these separated Teukolsky equations and the Green's function for a point source, how to calculate images from this Green's function, and then some results with a conclusion in an outlook to the Taub-NUT de Sitter spacetime. So, Kerr-de Sitter spacetime. So, for the completeness, I show you the line element for Kerr-de Sitter spacetime, which is in principle characterized by a mass parameter, a spin parameter, or Kerr parameter sometimes called, and a positive cosmological constant. The structure of this line element without a rescaling of the dt and d phi component causes like conical singularities. So we introduce here a psi factor by which these conical singularities can be completely eliminated, so they are just a coordinate appearance. So nothing which is very crucial for this spacetime at least. And then the functions of this metric are in such a way that we only have to focus on the delta R polynomial because the delta phi polynomial, because these are the only ones which are in the denominator and can cause singularities. So the singularities are known as the horizon in this case because it's from the choice of the coordinates here. And we have 4 horizons in this case: a negative cosmological horizon, a Cauchy horizon, an event horizon, and a positive cosmological horizon. And we demand that we choose our parameters in such a way that we have distinct and real horizon locations in order to prevent a naked singularity here. And this restricts the choice of our Kerr-spin parameter and of our positive cosmological constant in such a way that we have a parameter space which looks like this blue shaded area. So for our calculations, we will always be inside of this blue shaded area to avoid the appearance of naked singularities. Okay, so much for the Kerr spacetime. Teukolsky equation, calculation of Teukolsky equation is pretty rich in steps, so I will really tune it down to the most important parts. A usual approach for perturbations is like using a linear perturbation in terms of the spacetime. However, in the Newman-Penrose formalism, it is possible to reformulate the metric in many scalars and functions and identities. And then you take everything you have derived in this context and perturb this linearly. And by this, in the end, you will get a differential equation which looks like this in all of these Newman-Penrose scalars, which is also looking very complicated. And it is a second-order differential equation, partial differential equation for an yet unknown function psi. So psi is depending on t, r, theta, and phi. And for the physicality, so in the choice of a spin parameter here, this is, for example, also the advantage in using the Newman-Penrose formalism in this case, that we can now, we have no access to many test fields in order to analyze linear perturbations here. So if we choose S equals 0, we get the Klein-Gordon equation for scalar test field. We can get test neutrino fields, Maxwell fields, Harita-Schwinger fields, or, for example, linear gravitational perturbations. And by the choice of the spin parameter, we get a solution in terms of the Newman-Penrose formalism. So, which looks like in scalar here is encoding, for example, polarization, degrees of freedoms. So, later we will come back to this differential equation. So for convenience, I introduce this script D for the operator of this wave function. So, and if you insert everything from the Newman-Penrose formalism, you get this very messy differential equation. I don't want to go into detail, but I just wanted to show how it in the end will look like. And we are looking for a solution for exactly this differential equation. How is it done? In principle, by a separation ansatz where we can separate the time and azimuthal part in such a way away, because the space-time is offering this symmetry, but the radial and the polar part has to be kept in an yet unknown form for a function. So we are looking for a solution for these kind of functions. And radial Teukolsky equation is now an ordinary differential equation of second order for this unknown function R, and it is characterized, mostly characterized in a mathematical sense by the dr polynomial from the space-time. And we can see that this polynomial is decomposed in its 4 horizon locations, And but these are regular singularities of this differential equation. So this is not to be confused with singularities in a differential geometry sense, but in a like differential equation sense. This means that even though the differential equation will become singular at the horizon locations, we yet can still introduce a series expansion which is finite and regular at these points. This is what regular singularities for differential equation means. And this differential equation has in principle 5, but we can remove the one at infinity by a certain transformation. I will come to this back later. Yeah, the four horizons are the regular singularity of this differential equation, and we want to narrow down our region of interest to the so-called domain of outer communication. So we will keep our evaluation between the event horizon and the cosmological horizon. The polar Teukolsky equation has a very similar structure. It is also a polynomial inside of this parenthesis, which is characterizing the behavior of this differential equation. And 4 or 5 regular singularities, again, infinity being removable. And the region of interest are between x3 and x4, which in principle are our south and north pole. So this is also our region of interest where we narrow down now. The separation constant lambda introduced by the separation ansatz here is in the context of a Sturm-Liouville theory for differential equation and eigenvalue. So this is very important to solve later. And I want to give a very quick recap how it's done. The separated differential equations we now have here written in 8 and 9 are in principle Points equations. And this is why I have to lose some words what Points equation is. So, Points equation. It is a differential equation and the most general differential equation for ordinary second-order linear differential equations with 4 regular singularities. In a canonical way, it is written in equation 10, and then we have our regular singularities now at 0, 1, a, and infinity. A not to be confused with the Kerr spin parameter, but with the so-called singularity parameter for this differential equation. And A can take any complex value you can imagine. So. The 6 parameters characterizing this differential equation are the ones in the parentheses here. So these are the exponent parameters, and then we have an accessory parameter and 2 more infinity exponent parameters. So how to solve such a differential equation? You solve such a differential equation in such a way that you introduce a power series or a function series. And because the hypergeometric function roots from a differential equation, which is a special case of the Hoynes equation, it's very natural to choose hypergeometric functions in a function series for it. So by insertion of equation 11 into equation 10, you get a so-called 3 terms recurrence relation, and then you can evaluate for the CNs in order to get your coefficients of this function series expansions. What in principle is now being constructed is a so-called local Hoyne function HL. And it has the property that it's only converging in a circular radius up to the nearest other regular singularity. So this is like much information already putting in. So let me visualize it. The Z plane, the complex Z plane I want to show here is showing the regular singularities. And for the Z equals 0 plane, we have 2 solutions converging in this circular radius. However, this one is not included in the convergence region, so only this space is giving us information. The next thing, we have 2 solutions also at Z equal 1, but it is only reaching to the nearest other singularity. In this case, this would be the singularity parameter in this case. Okay, so local Hoyne functions. We can turn local Hoyne functions into so-called Hoyne functions, HF. And this is done by a specific derivation of the auxiliary parameter K. And this auxiliary parameter K, when it's fulfilling this equation here, then you can turn local Hoyne functions into Hoyne functions. Note that here is a notation used which is showing in principle continued fractions. So this is these two parts of the expression are infinite continued fractions. So this Q is now having an index K, which indicates that there are an infinite countable set of solutions by which we can transform the local Heuin functions into Heuin functions. And then this QK, because it's also appearing in every part of the continued fractions, we have to solve it by a successive approximation. So, and then what one has is that the Heuin functions now have two regular singularities in the convergence space, and in such a way that the convergence space now has the form of an ellipse with both regular singularities in its focal point and with A being on the edge, but A is again not in the convergence space. Okay, what else is so interesting about the Heuin function? The point is now that we can formulate for these solutions an orthogonality relation, and this orthogonality relation will give us a normalization constant. And this normalization constant can also be expressed completely analytic in terms of every solution we have from the Heuin functions now. So this is very important. Later I will come back to this when I discuss the Green's function for point scattering. Okay, so much for the Heuin equation, how to solve the separated Teukolsky equations in the end. This is done by taking our original separated Teukolsky equations, in this case the polar Teukolsky equation, and by transforming this differential equation to the Heuin form. This is done in two steps. We first transform the independent variable in such a way that our regular singularities now lie on 0, 1, A, and infinity. And then we transform the dependent variable by reducing every exponent in this form of equation 20. And in order to get to the Heuin's equation, A1 to A5 have to have a very specific form, and then you have the transformation done. Now you can derive the eigenvalue for this equation. As I've already told, we want to have a function for the polar Teukolsky equation such that we have regularity at both poles at the same time. For example, if I consider now the Schwarzschild geometry, then this differential equation gives the spherical harmonics. For Kerr-de Sitter, this is way more complicated. So we can use the information we have from the transformation to the Heuin functions. And for this, the eigenvalue has to have a very specific form, and we can use the successive approximation for this case, because the lambda is encoded through the transformation now in these Qs. So the successive approximation, the infinite approximation of this eigenvalue has this form, and for A equals 0, we get, as I already hinted out, spherical harmonics, and then the rest of these exponents characterize the eigenvalue we need in order to get Heuin functions for the Kerr-de Sitter spacetime. Okay, I mean, in principle, I have already discussed all of these points. It's a little bit over the top. So here, let me just say that the final solution we have for these polar solutions divided by the normalization constant I've just talked about, these will turn our solutions into a complete set of orthonormal functions. And then by this, we get a completeness relation. And this completeness relation is important when being used in the Green's function, because otherwise we won't have a converging series anymore. So this is very important for the solutions of the polar Teukolsky equations. Yeah. Spherical harmonics are gained by this limit. Spin-weighted spherical harmonics if we have a non-zero spin for our test fields, and spheroidal harmonics if we, for example, look at scalar wave perturbation with the presence of Kerr spin parameter. Then we have 4 solutions, because we have 2 regular singularities at each 4 solutions at 2 regular singularities, and we now have to look which of these expressions will be regular at the poles. And for this, you take a look at every solution you have and make a function series expansion for the north and the south pole, and you only take the regular one. So by the form these A's take, for the form the A takes, you only are left with two solutions left, and they have to fulfill these two conditions here for the index I and J. Okay, I will cover the radial solution very quickly. So in principle, what you do is the same as in the angular case. You transform independent and dependent variable to get to the Hoynes equation. And then the boundary condition in the angular case was regularity on both poles. Here you want to have the following. You set up an in and an up mode by which you demand that at the event horizon only incoming modes are allowed. And at the cosmological horizon, you only demand for the up mode that only outgoing modes are allowed. And then a specific set of local Hoyne functions will solve this boundary condition, and then this is done here in this case. Okay, Green's function, we consider now a monochromatic point source at a specific coordinate, and we omit the time dependence here in this case because it's only introducing a time, like a phase shift depending on the time coordinate. And then our differential equation looks like this. This is why I introduced this script D. And then the radial Green's function, which has to solve this differential equation, has to fulfill another property. It has to fulfill that both linearly independent solutions we got from the radial Green's function have to have the same value at the radial location of our point source, Rs. This is done by equation 29, and then you get a Green's function as in equation 30, which now can describe linear perturbations and wave optics in the case of the Kerr-de Sitter spacetime. And now we want to see wave optics. Because we will now first only use the scalar perturbation, so S equals 0, we can use the Kirchhoff-Fresnel approximation. And in principle, what Kirchhoff-Fresnel approximation for scalar field means is that if the source plane and the image plane have a high distance to the lens plane, then the Fourier transformation of the measurement on the lens plane will be the image plane. So we can just measure the lens plane, take the Fourier transformation of it, and then we have the information which we want to have on the image plane in this case. This is everything we have to do in this case. So yeah, I wanted to show an example on the next slide. Maybe this is becoming more clearer, but in principle, the scattering of a point source from a black hole will be scattered on some lens plane, and then on the lens plane you will have a interference pattern. This interference pattern by this thin lens approximation is then, in principle, being lensed on an image plane, and the image plane is then what you see. This, yeah, exactly. This like spoil at the beginning was the image plane. Yes, exactly. I will show it on the next slide. I guess it will become more clearer, but ask me then another time. So just let me. Observer plane is maybe a better, but yeah, for sure. It's not the black hole. Yeah, it's the observer. So you will construct a coordinate plane on which you then observe in the interference pattern I was just talking about. So I can show it on this slide. So this is, in this sense, my lens or observer plane, and this information encodes already my my image plane I want to observe. So, okay, the results I want to show. They implicate that we have scalar wave scattering. We choose a fixed set for observer and point radius, a fixed cosmological constant, and the size of this observer plane. So this is the observer plane in this grayish area. And unless stated otherwise, our point source is being located on the equatorial plane as well as the point source. And we evaluate 71 by 71 calculations on our observer plane here. And by the 2D Fourier transformation of this plane, we will get our image. And let me just say the magnitude of every image is normalized on its own maximum, so please be careful by comparison between the results I will show. And because the Green's function is in principle a series which goes up to infinity, I have to cut off at a certain capital L. And this capital L, we decided to introduce a heuristically motivated L. So the follow-up partial summations have to fall off under a certain condition, and then the convergence of the Green's function will look like this. So this red dashed line here indicates where we say, okay, it's sufficiently converged, but in principle you have to calculate it up to infinity. So there will be a very, 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 very minor error you use. So, okay. Yes. I also have a video, but I kept it out. I mean, if you're interested, I can show it you in the discussion. So, yeah. Okay, Kerr-de Sitter is now what I want to show in the beginning. So in the upper row, you see the imaginary part of the Green's function on the observer plane. And what you can see is by variation of the frequency that, yeah, I mean, the concentric circles of the interference get finer and finer, which is nothing which is very surprising. But looking at the wave-optical image formation, so the Fourier transformation of our Green's function, and then taking the absolute square of it, is showing that in this antipodal alignment I've just shown, the Einstein rings get just sharper and sharper. So this is something which is rather to be expected. But here you now see that it's not, like in the ray-optical case, a sharp ring, but it is a magnitude distribution which is coming from wave-optical image formation. So how it is looking like for the Kerr-de Sitter case, we start at the right side for the Schwarzschild case and introduce a rising Kerr spin parameter. And what you can see, even though the configuration stays fixed, the image shifts into a region and also gains symmetry breaking details. And how is it looking for the image plane? So what you can see, by keeping the frequency of our point source fixed and only altering the Kerr spin parameter, the image shifts into a direction. So what you can see here in the wave optical sense is like the frame dragging effect. And what one does not see is an Einstein ring or the typical Kerr length parameter. So what is the problem not seeing the shadow, for example, here? Is it maybe that the configuration of point source and observer is not correct? Well, I mean, you can compensate the frame dragging in such a sense that the point source is now located at a different azimuthal angle, and then you would get an Einstein ring for the Kerr spin for the Kerr-de Sitter space-time, but still no shadow of a Kerr black hole. If you look very closely, you might see it here in this interference in the inner ring, but that is not really convincing. So what is the problem here? The problem is the setup by taking only one point source. What I mean by this is that the shadow boundary curve is calculated for a ray-optical case in such a way that you have an observer and then you take the geodesics going backwards in time in such an angle that they hit the photon region. So this is in the case for a rotating black hole closer for co-rotating geodesics and far away for counter-rotating geodesics. And we are coming from a different perspective. We cannot calculate wave optics going back in time. So we have a point source somewhere and it's being scattered to our observer. So the problem here is that we only take one point source. We have to go up to multiple point sources. And we do it by this, that we take a point source on a half sphere antipodally aligned to our observer now, which we can do because our solutions are linear solutions, and the sum of these solutions is again a solution to our Teukolsky master equation. So and if you do it like this, then you get these results also for different spin parameters. For a Schwarzschild-de Sitter case, you have a circular hole, and as you ramp up the Kerr parameter, it gets more dented in this case. And so I mean, you get this interference pattern here in a darker region in the center here, and we plotted the ray-optical approach by this orange dashed line here in the picture, And let me say that for this case, we see an alignment of ray optical case and wave optical case such that we have a so-called zero angular momentum observer. So it's co-rotating with the space-time. We have no influence on that. Let me comment maybe on that later on the conclusions. So another part how you can control the shape of the shadow is by taking different locations of the observer. So the half sphere has to move with it in these like figures here. And then you see the same effect that the shadows co-moving with the ray optical results here. So one last thing I want to show, or maybe if I can skip if my time is too short. Okay, yeah, I can. Yeah, okay. Then I will.
There is a hard line
I see. Okay. 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 I mean, I can also hurry up if you want to. Okay. 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 Then I just want to show an additional thing which we like observed in this case. We have shown that this wave optical image formation works convincingly, and by taking different values, we also can see another thing which is usually not seen when you only take a look at gravitational lensing maps. For example, if now the formation is in such a case that we have our black hole rotating in this way, and we place our point source here and our observer here, then what one can see is that in this direction, in this configuration, the primary image is on the boundary of the shadow curve, and we have a second image here and a very faint third image here. And as you ramp up the curve spin parameter, you see that suddenly an image splitting is appearing for these fainter images here. And then you have suddenly not 3, but 5 images. So there are some literature about this topic for a weak rotational angular momentum case where they say that in such a configuration this splitting happens, but you do not see it in this lensing maps because, well, it's a very, very, very small feature here. If you really look at the results of these colleagues here and look at these spaces where the points should appear, it's a very, very tiny space where you can see that these regions are in fact showing these splitting images. But the thing is, you can see it in the wave optical image formation even better because the frequency or these infinite images of the primary image at the shadow boundary curve merge together, so they appear brighter. So this is why we show the same configuration for high frequency and then look at different frequencies, and then in this case, these 4 images merge into one, and they become brighter in this case. So this is why you can see them here and not in the lensing map. So this is something which is really very nice and complementing the lensing map approach. So what can you do from here? I mean, there's plenty of things to do. The grayish things are like not so important at the moment, but we have something like what is happening at different spin fields, a different approach to the observer because it's very idealistic, but also like extend to other spacetimes. And the most interesting thing which I want to conclude on is the Taub-NUT de Sitter spacetime, which we are working on. The Taub-NUT de Sitter spacetime is a spacetime which is having a so-called NUT parameter, and this NUT parameter can also be called gravitomagnetic monopole. And the reason for this is why it is very similar to the magnetic monopoles in many, many features. And it has also very interesting interpretations, so which always contain, for example, closed time-like curves or the present of the conical singularity here in this case, which can be eliminated if you go into the different interpretation. But then this is only possible by making the time coordinate periodic, and this is something which is violating, for example, causality in a crucial manner. So we are interested in how is the singularity behaving in the wave optical regime? Can you see it for lower frequencies, and how is it differing for these calculations? And for this, we have a different paper which is only focusing on the angular momentum or the angular Teukolsky equation, because you already can see the most properties in this case. For example, what we are focusing on quantization and scattering, because magnetic monopoles come always with the quantization of electric charge and the magnetic monopole. And we wanted to see, can someone derive it as well here in this case? And what we found out is that for the Bonner interpretation, this is not the case. So our completeness relation looks like this, and the decomposition of our radial coefficients is only done by these n. N stands in this case for the nodes of our harmonics, or not harmonics if you want to say it like this. The Miesner interpretation, on the other hand, has such a property that you have quantization. I think the better wording here would be discretization of the product of the knot charge and the frequency. So if you go up for high frequency, the sum will become very narrow. So it's also very interesting how this limit will calculate in the end. Okay, and now we have like a complete solution of this angular Teukolsky equation, how completeness relations form in this way. And we want to see in the future how, for example, here's a lensing map for a NUT spacetime, how these aforementioned conical singularities in the Bonner interpretation will behave for a wave-optical image formation. So let me come to my conclusions. We calculated wave-optical image formation for point sources by using the Hoynes equation and used the construction of complete orthonormal sets of functions. And the limits coincide with many other like observation data, with other theoretical results, and also could like reproduce the image splitting case as hinted by these colleagues here. So sorry for the long talk. With this, I conclude, and yeah, thank you for your attention.